Hi everyone, my name is Poom and my partner is Derek, and we are Cascading Blocks. And today we're going to talk about our final project. So the goal of our final project is to apply computer vision topics to create a fun project and learn about its potential. In addition to that, we hope to learn a new algorithm and approach for face detection and face tracking. And based on this goal, we came up with a game that goes as follows. So the players must move their face around to collect the green falling objects and avoid the red objects that drop randomly from the top of the screen. If the player's face hit the green objects, the score increases by 1. And if the player face hit the red object, the score would decreases by 1. The goal is to get the highest score within 30 seconds. In addition to that, the highest score would be maintained across the games. And in order to sort of like implement the game, here are our design approach. First, we need to detect the face. And after we detect the face, we then would use another algorithm to track the face. More specifically, we would first detect the face with hard cascade algorithm, and then we track the face with CSRT tracker algorithm, which both of these we can utilize from the library from OpenCV. Lastly, after we are able to detect the face, we would be able to draw the bounding box around the face. We would use that bounding box, the coordinate of the bounding box, to calculate the collision, whether our face is collineed with any of the falling objects that drop randomly from the top of the screen. Now, we want to talk about what are the difference between face detection and face tracking. Why did we choose to do both ways? So in our first approach, initially we thought that with only face detection in each frame, it would be good enough. So we thought that, okay, we probably can just use hard cascade algorithm. However, after in the first approach, we found the inconsistency in our results. More specifically, it was not able to handle rotation in the face. And every time when we rotate the face, the bounding box was kind of like going away from our face. And in addition to that, if we only use face detection alone, the computation for that is pretty intensive. And therefore, we decided to combine hard cascade algorithm with CSRT tracker. More specifically, we will first detect the face to draw an area of interest, and then use that area or the bounding box of interest to then use that as a prior to calculate probability of the posterior that we learn in class with the CSRT algorithm. We will talk more about this algorithm later. And now let's go into the algorithm themselves, which first is the face detection. So the idea of the face detection is that we would use the search window that do a raster scan through an image. So you can see here, the search window kind of like go through each pixel and try to like extract the feature from each pixel. And based on that feature, we want to determine whether that is face or not face. So now, here's a more detail about that. So for each of the search window, we would extract the features, and then we would use a classification model to determine whether those features, based on those features, that search window is face or not face. Now, the question is, what are the good characteristics of those features? The good features, obviously, needs to be able to discriminate between face and non-face. And then it should be able to compute really fast. And the answer to this question on like what would be good features is the hard features. The hard features can be computed by hard filters, which you can see here. There are a little square. We might have learned in class that the first two square in the top row are for the edge detection, and the third one would be the line detection. Derek would explain more about how we calculate these hard features.
Right, so the computation is actually pretty simple. It's actually the summation of the pixels in the white area, their intensities, minus the summation of the pixel intensities in the black area. But the issue is that this becomes increasingly expensive per feature, per sub area within our image. And so on here, this next slide, you can see there's something called an integral image. And that's the idea that instead of taking these costs and taking some summation each time, we can find it very easily using an integral image rectangle. On the bottom here, the A, B, C, D, E, F, those are the kind of hard features that you can imagine with C. Cool. And so because that's a lot of features, a faster way to speed up this algorithm is using something called an ADA boost. And the idea behind this is that we're going to combine a ton of weak features, weak classifiers, to create a strong classifier. And thereby, we reduce the amount of features that we're calculating and needing to compute, and instead focusing on the ones that are important and creating a strong classifier that way. And then still we're left with a ton of features, and that's the final step of the hard cascade algorithm, to create a cascading classifier. So these are made up of a series of stages, and each stage is made up of weak learners trained through the boosting. And so we're going to create a final output of a collection of weak learners that are strong together. The classifier then decides whether each object was located successfully or not in the current region, in our case being a face. And if it is, if it wasn't successfully found, we move on to the next region. Cool. And here's kind of a video showing how this might work in a real image. As you can see, it's going through all the different hard features per subregion within the image. And in about the middle of the video, you'll see that the face has actually been detected. And so we actually mark that region as a region of interest. And we continue. And so that's how you can see a bunch of weak learners eventually become a strong collective.
All right, now that we learned about face detection, after we detect the face and know where to look at for the face, now we just need to use that area of interest as a bounding box, as a template for to track the face. Now, while there are so many tracking models out there from OpenCV, we realize that CSRT is one of the best tracker model out there. That's why we utilize it. And more specifically, this CSRT model utilizes what is called spatial reliability maps for adjusting the filter support to the part of the selected region from the frame for tracking. So as you can see here in the picture of a person here, initially we use the area of interest to calculate the spatial prior, and after that, we were able to calculate the probability of around the region, which we call back projection. Based on these two probabilities, we sort of like able to calculate the posterior of where the probability of the face should be, and then we outlaying the training region, which we can create we can then track the face. This has proved to increases the accuracy of the searching area and is able to track non-rectangular objects, which is the face. More specifically about CSRT, CSRT uses only two standard features, which is the first one is histogram of oriented gradients, which are the magnitude of gradients and the direction of gradients. And in addition to that, it uses the color from the image. While CSRT only uses two standard features, it gives really high accuracy for object tracking. So now we understand about CSRT a little bit. Let's look at the pros and cons of it. The pros of CSRT is that it's more accurate than most of the tracking models. It's also robust to unpredictable motion. For example, if I move my head really fast, it still will be able to track my face. In addition to that, it can recover from failures and report unrecoverable failures. Now let's talk about the bad thing about CSRT. CSRT cannot recover well from failures due to full occlusion. And because of this, to solve this problem, our model or our project is use the face detection to help solve this problem. Every time when the CSRT doesn't work, we trigger the face detection from high cascade algorithm to find a new area of interest, and which is the face. After we have the face, we would then use CRST to help with this afterwards. Lastly, while CRST have a lot of good things, it's still slower than other tracking model. However, for in our game, we don't need to have that too fast algorithm. Now let's talk about the demo.
So here's a demo of me playing the game. And as you can see, I'm moving my head side to side, and it's able to successfully track where my face is. And you can actually see that at a couple different points. I exit the frame just like that. And when I do, our face detection takes over when I re-enter the frame. It detects my face, and it's able to track where I am using the tracking algorithm afterwards. And you can see that I'm moving my head around, and I'm actually curving my head left and right, and it's able to find where I am throughout all the game. And so now I'll be talking about the future work. We want to explore and incorporate other potential facial detection algorithms and tracking models into our game. And that way we can compare which one does better or worse in our particular case. In addition, we'd like to incorporate detection beyond just faces. One idea that we had was performing gesture detection, seeing if it would be able to recognize when you did particular motions with your hand or with your body and stuff like that. We also would like to make this a multiplayer game so that it's not just restricted to just one player, but instead could have multiple people playing at the same time. And we'd also like to increase the difficulty of the game as the game progresses.
Right. Thank you.
Thank you.